Alright, welcome everyone. In today's video, we're going to talk about vibrational rotational spectroscopy. So, right, when light is shined on a molecule, that light technically can induce a change in vibrational state, rotational state, and electronic state at the same time. Okay. Now, it's not necessarily always going to, but it can, right? And so, right, for vibrations and rotations, okay, these often are linked together, okay? And you can think of the reason why, right, it's just the fact that, right, changing your vibrations, right, if a diatomic molecule here, right, HCl, right, I change the distance between the HCl, right, that changes its moment of inertia, right, which is that reduced mass times separation distance squared, okay? So as this is vibrating, the moment of inertia is changing, right? So this change in moment of inertia will change the rotational states. Similarly, as you're rotating faster and faster, that's going to stretch your bond a little bit, and that's going to change kind of your vibrational frequency and your bond strength and other things like that. And so there's this direct link between vibration and rotations, okay? Right. And in lab, you go a lot more into detail than we'll kind of talk about here in this lecture about kind of the anharmonic effects and the extra peaks that occur due to the coupling of vibrational and rotational states. Okay. So for the general selection rules for vibrational rotational transition, they're the same as a pure rotational transition and a pure vibrational transition, right? Right, so the selection rules is the molecule has to have a permanent dipole moment, and the vibration must change that dipole moment. Okay, right. The specific selection rules is that the vibrational quantum number and the rotational quantum numbers can change at most by 1. Okay, and we'll note here if you have a diatomic molecule, right, and if it has some orbital angular momentum across the bond, i.e., it has something like a pi bond, right, so like CO, right, for example. Then it is possible to have delta J equals 0. Okay, so this is possible, right, for something like HCl. This is not possible. Okay, but otherwise, the selection rules are the same as vibrations and rotations, right? We're just now doing these changes together. Okay, so we're going to first talk about when we're, say, absorbing energy in the vibrational state. So delta V is +1, right? And when we do that, we can break up this vibrational energy change into 3 potential branches: R branch, P branch, and Q branch. Okay, right? So Q here is 0, P is related to delta J is -1, and R is delta J +1. Okay, so we'll talk about this. So Q RS, and then P O. Right? Yeah, sorry, I'm doing my alphabet here, right? Trying to do the alphabet backwards, right? So Q, right? So for these values, the change in delta J is 0, right? 1, +1, +2. It's going to be -1 and -2. Okay, and so because we'll talk about Raman spectra, and in Raman spectra you can have a change of ±2, and so we'll talk about an S branch and an O branch. Okay, and so the labels of these branches, okay, O, P, Q, R, S, are related to essentially alphabetically how they appear. Right, Q is defined as 0. Okay, Q is when there's no rotational change, and then as you go up the alphabet, your change in your rotational quantum number increases by 1 from R equals 1, S equals +2, T would be +3, so on and so forth, right? As you go down the alphabet, P is -1, O is -2, right? So this is just a convenient way, and when we talk about Raman rotational spectra, I'll talk about this again, okay? But it's a convenient way to try to remember, right, the P, Q, and R branches. What do they refer to in terms of the change in the rotational quantum number, right? The vibrational quantum number is just +1, in all three cases. Okay. So the energy difference for these changes in states is going to be related with the change in energy for your vibrational rotational energy here, right? So this energy, which depends on the vibrational and rotational quantum number, right, is just the vibrational energy plus the rotational energy, okay? Right, we're not including any higher order effects here, okay? But you can include higher order effects, right, due to the coupling of these rotational and vibrational states, which is done, for example, in lab. Okay, so, right, if we want to look at, say, the R branch, okay, which has delta J as +1, okay, then what we're looking at is we're looking at this energy difference, which is V plus 1, J plus 1 to E, to Vj, okay? So just plugging in those values, right, and simplifying, we get this equation here, right, which is the energy change related with the R branch, which is just Hc times the vibrational constant, okay? And so this is the vibrational constant, and 2hcb, which is your rotational constant, right, times J plus 1. Right. For the P branch, you have delta J is -1, so you're going from EV plus 1, J minus 1 to EVJ, and then you get this equation here, which is HCV plus 2 HCB times J. But note here, J cannot equal 0 because you can't go right from J equals 0 to J equals -1, right? This ain't happening, okay? So J cannot be 0. So this is the energy change that's related with the P branch. So these are the energies in which you would see peaks in a vibrational rotation spectra for the P branch. Finally, the Q branch, right? There's no change in J, so the J terms just cancel with each other, okay? And you're just left with your vibrational peak, right? Which is what you should find, right? If there's no change in rotational state, then your peak should just be at the same peak location that you'd get for just a normal vibrational transition, because that's all that's going on in the Q branch. You just have a regular vibrational transition. So, right, looking at then what this peak looks like, right? So here, what's plotted is the vibrational state V1, and vibrational state V0, and then there's a bunch of rotational states. So these are the J values, right? For so we'll call this like J prime and J double prime, right? These are the J values for the V equals 1 vibrational state, and these are the J values for the V equals 0 vibrational state, right? And so again, for the Q branch, you keep what rotational state you're in and just go up into the same vibrational state. So all of these peaks will be right on top of each other, and you just have one peak for the Q branch, right? Which that one peak is related to a pure vibrational transition. Sorry, something messed up with my pen here. Pure vibrational transition. Okay, right, and then again, the P branch is when, right, delta J is equal to -1, right? So you see here, for example, I'm at the highest J state here on this very left peak, and I go to the second highest J state here when I go up in the vibrational state, okay? And so, right, and so that's what each one of these different peaks are corresponding to, is going from different J states within the same vibrational transition, okay? And then the R is going to be the same thing, right, where now I'm going right up in my J values. So I'm starting, say, for example, J equals 0, and going up to J equals 1, right? And looking at, right, what that peak is, okay? So sort of just like, so let's change my pen color here. So just like in pure rotational absorption or emission spectrum, right? what you have is the energy difference between these different peaks, okay? The energy difference between those different peaks, that delta E, is just equal to 2hCb. Okay? So the splitting between those peaks is related with your rotational constant, okay? Right? Right? Which is the same as the splitting between the Q and the first peak in the P, and the same in the splitting between Q and the first peak in the R. Okay? Right? Now, for example, if there's no Q, right, let's say I'm looking at HCl, right? If I'm looking at HCl, right, then there's not going to be any Q branch, right? But what I can do is I can take my lowest energy peak, if you will, for the R branch and subtract 2hCb from that to get where the Q branch will be. Okay? And so that will be it for the vibrational and rotational absorption and emission spectra. Okay? Just note here, right, that the emission spectra is the same type of thing as the absorption. Okay? The emission spectra is going to look the same type of thing as absorption. It's going to be P branch, R branch, Q branch, all kind of the exact same type of thing. So energy differences are all going to be the same. So it's not really, won't really redrive all of it because it ends up being the exact same. Okay. And so next we will start talking about vibrational rotational Raman spectra in the next video.